So we're going to go ahead and begin. This is electrochemistry class for the advancing lab group. And it is going to be pretty much a traditional kind of lecture class, except I'm going to heckle the audience for audience participation as we go along. You'll see what I've done. I see Eve brought a copy of Faulkner. That we're going to basically work our way through some of the beginning chapters of Faulkner, and then on Thursday we will specifically try and tie all that into FSCB. So my goal, I wrote the schedule out in room 128. Today, my goal is to do chapter 1. Then tomorrow, we're going to go approximately 2 and 3. I don't know that we'll finish chapter 1 today. I'll talk about that. So if we don't, we'll finish it tomorrow. Wednesday, we're going to approximately do chapters 4 to 5. And Thursday, I didn't write it all down. Chapter 6. And then we're going to do a section 11.7, and then no section 14.3. And then we'll do FSCB, which isn't really covered in the textbook. So my goal in doing this class is to teach you textbook electrochemistry. It's not particularly to teach you FSCB, and the reason I want to teach you textbook electrochemistry is because we don't do textbook electrochemistry. But what does everybody in the world know? If you're going to talk to somebody about textbook electrochemistry, they assume that everything you do in electrochemistry should be like the textbook, right? So if you're talking to another professor, even if you're at a conference, what little people know, right, is the textbook. And so when everything we do, for the most part, violates the textbook, we'll talk about that as we go along, we need to know that this is all like special case scenarios and not the way things really should be going. And so I don't do you any favor if I don't teach you textbook electrochemistry, even if we don't do textbook electrochemistry, because that's what everybody expects. So you need this as your frame of reference, right? Because everyone thinks this is your frame of reference. And I'll talk a lot about your oral exams. If you're an undergrad, it doesn't matter necessarily. But if you wanted to do a senior thesis or just talk to somebody at a conference about your research, you could more broadly think of it than just oral exams. You have to have this frame of reference for what we're doing. Okay, so we're going to do, this textbook is kind of like, there are other textbooks out there. It's by far probably the most popular one. Bard is ancient. He was here a couple years ago. A kind of ancient elder statesman of electrochemistry. Faulkner, I think is retired now. He was an electrochemist for years and years at the University of Illinois, then started climbing the administrative ladder, and eventually became president of the University of Texas at Austin. He's a well-known guy too. I think most of the edits and updates in this newer edition, they had like a 1980 edition. They didn't do anything with it until maybe 5 years ago or something. There was about a good 25 years where everybody still used this textbook, but it had never been updated. I don't think Faulkner did much of that. He was president of Texas at that time. Probably wasn't. But anyways, this is a textbook that kind of everybody knows in the field. Is it the best one? I don't know. Royce Murray, who used to be the editor of Analytical Chemistry, said his big fault with this textbook is always that there's not a lot of chemistry. It's an electrochemistry textbook that doesn't have a lot of chemistry. Sure does have a lot of math. So I'm going to try and help you make sense of all of that. But again, it's just a good starting place. It's kind of like what if we had a graduate level class in electrochemistry, it'd be the kind of default thing to teach from. So I'm not saying it's the end all be all, as I said. What it probably lacks is a lot of chemical examples of what you're seeing. But that's kind of things. All right, so the textbook is set up in a way that if you were to only understand chapter 1, you'd be doing really well. Because some textbooks start off with the happy-go-lucky text chapter that tells you nothing, and then you get on to the meat chapter 2. Not this textbook. This textbook takes the approach of we'll try and hit on every topic in a cursory manner in chapter 1, and then the rest of the textbook will expand upon these topics. So it's almost like general chemistry, right? Where we kind of hit everything in a general manner, and then the rest of your career in chemistry class, right? Is learning those things more in depth. That's how this textbook is set up. So we're going to do chapter 1 today. There will probably be some repetition as we go throughout the week. But I also want to clue you in that if you're like, what are the most important things to know? It's chapter 1. I'm not kidding when I say it's chapter 1. It's all in there. And if you really understood chapter 1, you'd be far, far ahead in your electrochemistry knowledge, quite frankly. So if you read anything, please read chapter 1 as we go through it kind of today. As we Okay, so with that said, I'm going to erase the sketch. Hopefully you're all start today talking about the electrochemical cell. It's where everybody sort of begins. So when you talk about electrochemistry, you have to realize that what's really important in electrochemistry is the junction of the electrode and the solution. We're not going to talk in this little class about any bulk methods. So everything that we're interested in is going on at the junction. Meaning, if you have, an electrode and you have stuff in solution out here, if your molecule sits out here the whole time, if it never sees the electrode, nothing happens to it, right? It's got to get to the junction before any electrochemistry can take place. So electrochemistry is a junction method, an interfacial method at heart, and so that differs from some other sort of bulk kind of reactions that you might have studied in physical chemistry or in other places like that. And so, with our electrode, and this is what I'm going to use as our drawing for an electrode. It's very high-tech, a line with a slash. That means electrode. You'll see it often. Right, the electrode is where we apply a voltage, right, where we exchange our electrons, et cetera, et cetera. So everything kind of happens at this junction. All right, so out here in solution then, we might have analytes, but we also normally have what we term an electrolyte solution. So electrolyte are just the ions in solution. So what are those ions? H plus, sodium, potassium, chloride, etc. on down the line. We don't think a lot about electrolytes, quite frankly, in this lab. But if you were making batteries, you would. So I have on occasion been in electrochemistry meetings and he's like, what do you think the effect of the electrolyte is in that? And I always have to say, let me think about that for a minute since I never think about that. But what's our favorite electrolyte solution? We use a buffer ion. I think some people use phosphate buffer saline, some people use tris, whatever. Approximate concentration of sodium chloride in your buffer. Anyone know? I'll take a range. I'll even take an amount per liter, or like grams per liter, or millimolar. Come on, you did this like twice a week.
7.6 grams per liter?
Yes, the number I had in my head is 8 grams. 8 grams of sodium chloride in that liter, right? You are making salt water. If that's never occurred to you, you are making salt water, 8 grams in 1 liter. That's a lot. So we don't worry too much about electrolyte concentration. You have a lot of ions. Luckily the body, right, we're trying to mimic those concentrations in the brain, and that's what so your brain has a ton of sodium in the extracellular space. So we don't worry about electrolyte, right? We try and match our electrolyte solution that we make in the lab to what we think is going to be in the brain as far as concentrations. But we have super high concentrations, so we're not going to be limited by electrolyte. But in case, if you never thought of it, we call buffer or that kind of thing, or even brain tissue, quite frankly. And if you're a battery chemist, you call it electrolyte. It is electrolyte. We just don't typically use those terms. So we want to look at that. If you were designing an electrolyte, you would want ions in there that move easily. And we'll talk a little bit today about IR drop and the effect of that. But you want these ions to be able to move easily so the solution is not resistive. So we'll be talking a little bit more about that. So again, we're going to have these ions, sort of electrolyte all around in our little solution, and they're going to be moving around in the solution. And we've got to have that because we've got to offset. You can't just, it's all charge balance still comes into play. You can't just apply a voltage over here and expect the solution does nothing, right? You have to balance charges. So we've got to have some charge things. So your analyte does not have to be charged, right, for electrochemistry. Don't mean typically is, but we don't have to have a charged analyte, but we've got to have some charged ions, an electrolyte, in that solution to make it work, to balance all of that. Okay, so with all of this, I've drawn you one electrode in solution, and that is not an electrochemical cell, right? I haven't gotten to my title yet, right? So to have an electrochemical cell, right, we always have to have a minimum of 2 electrodes. And the simple reason is this: you can do nothing with voltage. You cannot apply voltage or measure voltage. Doesn't matter which kind of experiment you're trying to do. Absolutely. Meaning there's no absolute voltages that you're going to be able to apply. Anyway, this is physics, right? If you take physics, you never just measure the voltage, right? You always have to hook up another lead to ground. Well, in electrochemistry, we don't call the second lead ground, right? We call the second lead, the second electrode, right? We call it a reference. But there is no such thing as absolute voltage, right? So there's never just one electrode. Now you all sit here and you nod your heads, but there are people out there, sadly from this lab, who have not answered questions like this correctly in their oral exam, and they have not done well. When they say, describe your electrodes, and they never get to a reference, and they're like, well, how do you complete the circuit? I don't know, what do you mean complete the circuit? And then you kind of go in this circle, and it's like, the poor professor is suffering mightily, going, just say there's a reference, right? There's got to be a reference in there. And so it's easy to forget about it, but you can't forget about it. It has to be there. And so we'll talk about the purpose of reference electrode and reference electrodes a little bit more, but the reference electrode, again, is something to measure voltage against. If you have nothing else, at this point in time, we'll say it's to measure voltage against. All right, so let's remind ourselves of what voltage is. People in this room have taken my electrochemistry, my electronics portion of my class. Who has a good definition of voltage? Shane, Hillary, you're not, exempt from this question, having taken my class.
Voltage is the energy you can push the electrode more.
Okay, that's not a terrible definition. The real definition that nobody ever seems to really memorize unless you teach this like every year, like I do. Yeah, it's an energy and that kind of thing. The real definition of voltage is work done to separate charge. This is my favorite definition of voltage. Because a volt is actually a joule per coulomb. So joules, right, are work, and charge on electrons can be so I'm nice the first time. Volt, joule, coulomb. So you're separating charge. So if you think about it, back to our kind of electrode, right? As we apply a voltage here, right, we are moving electrons. That's a process of sort of separating charge. But, it's not my notes, we're going to do it now. So what's the difference between voltage and current? What is current? Current's the easier one.
Movement of electrons?
Yeah, so current is the movement, the flow of electrons. So voltage, I never want to hear anyone using voltage as in, like the electrons, I apply, 1 volt is, electrons moving. Voltage is not moving. Chang's definition of voltage actually works pretty well for electrochemistry. It's the potential, the amount of energy you need to apply to get them to move, but it's not them moving, right? The rate that they move is current. And again, it may seem stupid for me to stand up here and try and beat these into you, but I'm going to try and beat these into you, because if you don't understand the difference between voltage and current, then you're going to really not go very far down the electrochemistry, the actual understanding of electrochemistry, because they're kind of fundamentally different things. This is work, kind of in an energy unit. This is flow, right? So the unit is an ampere, and that's coulombs per second. So the amount of stuff that's flowing. So again, we got to get some of these basic definitions down, just so we're going to look at. Right, and so as I said, work done to separate charge, or here's my other definition that I'll give you for voltage. And for electrochemistry, basically, you could say it's the energy to drive electrons, basically, or drive electrons between the electrons. So it's the energy that you need to cause this electron transfer sort of to happen. That's probably better. Okay. So, let's talk notation. Again, this is an example of stuff that we never use in our lab. So you say, why? You should bother to cover it because it just pops up all over the place. And if you're in electrochemistry, you ought to probably know what they're doing. So, right, you'll see people talk about electrochemical cells, and they'll write something like this. This example again is from the textbook. Something like that. And they're like, that's my electrochemical cell. And you may have learned this, quite frankly, in some sort of undergraduate class where they think this like notation is vitally important, and I'm literally an electrochemist and never use it. So, you know, that's part of it, right? But what it means, right, each of these slashes there, right, is a phase boundary. Right, so in this case, we have a solid zinc electrode that's in an electrolyte of aqueous zinc chloride. And then we would have solid AgCl that's next to a solid electrode. So again, if it's comma, they separate two things in one phase. And so sometimes you'll see this for a full, like this is one electrode, this is two electrodes, that's a whole cell. Sometimes you'll see a double line. That means that they're a complete phase boundary, meaning those solutions, they're on like in different solutions. Again, we won't go through the whole thing, but you should kind of know that these are phase boundaries and how you would interpret it. For instance, let's look at another one. This is just a half cell, right? So if it's not two electrodes, it's a half cell a reaction. So this is a half cell reaction. This reaction looks familiar to everybody, right? Silver. So we have silver chloride in a solution with potassium and chloride ions. When do we see that in our laboratory? Yeah, the backfill's not what exactly I'm looking for. Although you're right, I guess it is. What else do we use with silver chloride? The reference, right? So this is the notation for a standard silver chloride reference electron. Right, so if somebody were to write it all out, now we don't exactly use the standard because we don't control like the concentration of these. So if we'll talk about pH electrodes somewhere somehow. I think they come up in chapter 2. It's a weird part of chapter 2 that I don't think goes with the rest of the chapter, but hey, we'll do it anyways. I'm going to talk about ion selective electrodes. You know, so if we had it in a separate solution, we would control this really well. When we put it in the brain, obviously we don't control the potassium and chloride very well, but it works pretty much the same way. So this is our standard sort of reference electrode. Okay, does anyone know the potential of a silver chloride electrode? Relative to hydrogen. Can anyone get me in a
volts?
what?
0.3 volts?
That's high.
.197.
0.197 comes the expert from the back of the room. Yeah, I mean, all right, I'll let you round off. I was hoping someone would tell me 0.2. So it's about 0.2 volts, again, compared to what I'll call the standard hydrogen electrode. So I'll define the standard hydrogen electrode, and then we'll get back to that. The two most popular reference electrodes tend to be silver chloride, and then in the olden days, a calomel electrode. So calomel electrodes are made of mercury. So they've kind of gone out of fashion. But luckily for everybody, Calomel electrodes and sodium chloride electrodes are both around 0.2, so you can kind of switch back and forth and the potentials don't shift that much. So when in doubt, that's reference electrodes about 0.2, because most of them that are commonly used are. That's what you'll find. Okay, so I told you that there are no absolute voltages, right? So when somebody asks me, compared to what, that's always a great question, right? And so because we don't, like again, in physics, when you build circuits, it's the ground, right? Whatever the potential of the earth, that's ground, that's, 0. Well, in electrochemistry, somebody had to define it, right? And I don't know who decided this was, they probably have regretted it ever since, but this is what they decided. This is the rotation for the standard hydrogen electrode. So this is called either the standard hydrogen electrode or the normal hydrogen electrode. And I don't know the difference between them, really. They're the same. But you'll either see it called SHE or NHE, whatever, same notation. And so they decided that as you bubbled in, basically, you bubble in hydrogen to an acidic solution, and you have a platinum electrode. As you bubble in one atmosphere, so you have an activity of one atmosphere of hydrogen, and you have an activity, these are activities. So it's a concentration activity, to be absolutely correct, of 1 of hydrogen ions in solution. The reaction you would get there would give you, if that's defined as being 0. So this is defined as 0 in electrochemistry. And it's unfortunate only because who's really going to do that, right? I don't know who decided this was the end-all be-all, but they did, and it's been used for years. So. So we're never going to bubble hydrogen right into the brain of a rat. It's a reference electrode, thus, we need other things. And so, again,